Dynamic environments and unlinearity. The basic setting assumes risk-neutral agents with quasi-linear utility functions such that an agent acts to maximize the expected difference between its value from a sequence of decisions and its total payment. Consider discrete time periods t equals to 1 to 3 and so on, indexed by t and possibly infinite. A mechanism makes and enforces a sequence of decisions k equals to k to the 1, k to the 2, and so on, which is an O, with a decision k to the t made in period t. Let k to the closed interval between t1 and t2 equals to k to the t1 and so on to k to the t2. The decision made by a mechanism can depend on messages, such as bits received from agents as well as uncertain events that occur in the environment. For example, in a sponsored search, the realized supply of search terms determines the feasible allocation of user attention to advertisers. An agent's type theta I equals to AI diwi, which is in capital theta I, where capital theta I is the set of possible types. For agent I defines a valuation function via of theta ik, which is in R, on a sequence of decisions k and is private to an agent. Time periods ai di in t denote an agent's arrival and departure period, and via of theta I k equals to via of theta I and k to the closed interval between ai and di, i.e. an agent's value is invariant to decisions outside of its arrival-departure window. In addition to restricting the scope of decisions that influence an agent's value, the arrival period models the first period at which the agent is able to report its type to the mechanism. The valuation component wi, capital Wi of an agent's type, where capital Wi denotes the set of possible valuations, parameterizes the agent's valuation function and can be more expressive than a single real number. For example, in an online combinatorial auction, this needs to convey enough information to define substitutes. For example, I want item A or item B, but not both. Or complements, I only want item A if I also get item B. Preferences. Nor does the valuation need to be constant across all periods. For instance, an agent could discount its future value in a future periods t greater than ai by discount factor gamma to the t minus ai for gamma, which is chosen between 0 and 1, which is an open interval. Direct revelation mechanisms. The family of direct revelation online mechanisms restricts the message that an agent can send to the mechanism to a single direct claim about its type. For the most part, we consider closed mechanisms so that an agent receives no feedback before reporting its type, and cannot condition its strategy on the report of another agent. The mechanism state little h to the t, which is in capital H to the t, and where the capital H to the t is the set of possible states in period t, captures all information relevant to the decision by the mechanism in that period. Let omega, little omega, in capital omega define the set of possible stochastic events that can occur in the environment, such as the realization of uncertain supply. This does not include the types of agents or any randomization within the mechanism itself. Write capital omega equals to pi of omega to the t, where little t is in chosen among all the possible capital T, and let omega to the t is in capital omega to the t. Denote the information about omega that is revealed in period t. Similarly, let theta to the t denote the set of agent types reported in period t, and given this, it is convenient to define that h to the t equals to theta to the 1, theta to the 2, and so on to theta to the t, omega to the 1, omega to the 2, and so on to omega to the t, k to the 1, k to the 2, and so on to k to the t minus 1. Note, here is k to the t minus 1. In practice, the state will be represented by a small, sufficient statistic of this information. The state space H equals to the unions of H to the T, where this T is the unions of the ordered index T, may be finite, countably infinite, or continuous. This depends in part on whether agent types are discrete or continuous. Let K of H to the T denote the set of feasible decisions in the current time period, assumed finite for all H to the T. Let I of H to the T denote the set of active agents in state H to the T, i.e. those agents for which T is in the closed interval between AI and Di, that is the arrival time and also the departure time of agent I. Definition 16.2 Direct Revelation Online Mechanism. A direct revelation online mechanism M, which is defined as the tuple pi x, restricts each agent to making a single claim about its type and defines decision policy pi equals to the set pi to the t, where t is chosen among capital T, and the payment policy x is equals to the set x to the t, again where t is chosen among all the possible capital T, and where decision pi to the t of h to the t is in k of h to the t is made in state h to the t, and the payment xi to the t of h to the t in R, which is a real number, is collected from each agent I, which is in capital I of h to the t. Decision policy pi may be stochastic. The payment policy may collect payments from an agent across multiple periods. For notational convenience, we let pi of theta omega equals to k to the 1, k to the 2, and so on denote the sequence of decisions, and pi of theta omega in R denote the total payment collected from agent I, given type profile theta, and a realization of uncertain events, little omega and capital omega. Now example 16.3. Consider the canonical expiring items in experiment. Environment is the state H to the T can be defined as a list of reported agent types that are present in period T, indicating whether each agent is already allocated or not. Decision K, which is in capital K of H to the T, decides whether to allocate the item in the current period to some agent that is present and unallocated. Limited misreports constrain the strategy space available to agents in a direct revelation online mechanisms. Let's see definition 16.4, which is a limited misreports. Let C of theta I, which is in subset equals to capital theta I, for little theta I, which is in capital theta I, and that this C of theta I denote the set of available misreports to an agent with true type theta I. In the standard model adopted in offline MD, it is typical to assume that C of theta I is equals to capital theta I. So that means the misreport can be defined as the exactly capital theta I. We should assume no early arrival misreports, with C of theta I equals to the set theta I hat, which is defined as the tuple AI to the hat, Di to the hat, and omega I to the hat, such that AI is less than equals to AI to the hat, which is less than equals to Di to the hat, and omega I to the hat is in capital omega I, i.e. agent I cannot report an earlier arrival because it does not know its type or know about the mechanism until AI. Sometimes we should also assume no late departure misreports, which together with no early arrivals provide C of theta I equals to the set theta I to the hat equals to AI hat, Di hat, omega I hat, such that AI is less than equals to AI hat, less than equals to Di hat, as equals to di, and omega I to the head is in capital omega I. For example, we could argue that it is not credible to claim to have value for a ticket for a last-minute Broadway show after 5 p.m. because the auctioneer knows that it takes at least 2 hours to get to the theater and the show starts at 7 p.m. We strict attention to mechanisms that are either dominant strategy or Bayes-Nash incentive compatible. Let theta minus I equals to theta 1, theta 2, and so on till theta I minus 1, theta I plus 1, and so on. And capital theta minus I equals to the pi of capital theta j, where the multiplication is for multiplying all the index j, which is not in I. And the c of theta minus I is equals to pi of c of theta j, where the multiplication is for multiplying all those j, which is not in I. And consider misrepresents theta I, which is in capital C of theta I. Now let's see the definition 16.5. DSIC. Online mechanism M equals to the tuple pi x is dominant strategy incentive compatible DSIC, given limited misrepresents C if vi of theta I and pi of theta I theta minus I to the pi omega minus pi of the same parameter theta I theta minus I to the pi omega which is the difference of the output of vi and pi function is greater than or equals to vi of theta I pi of theta I to the head. Here we substitute theta I to the head and theta minus I to the pi omega. Then minus pi of, again we substitute theta I to the head and theta minus I prime and omega. This is for O theta I to the head, which is in C of theta I, O theta I, and O theta minus I prime in C of theta minus I, and O theta minus I in capital theta minus I, and O omega in capital omega. So it will be convenient to also adopt the terminology truthful in place of DSIC. The concept of DSIC requires that an agent maximizes its utility by reporting its true type whatever the reports of other agents and for all stochastic events omega. When the decision policy itself is stochastic, then DSIC requires that the expected utility is maximized from a truthful report, whatever the reports of other agents, and again for all stochastic events omega. A randomized mechanism, i.e. one with a stochastic policy, is said to satisfy strong truthfulness when truthful reporting is a dominant strategy for all random coin flips by the mechanism and for all external stochastic events omega. For Bayes-Nash incentive compatibility BNIC, we assume in addition that all agents know the correct probabilistic model of the distribution on types and on certain events, and that this is common knowledge. Definition 16.6 BNIC. Online mechanism M, which is equal to Q pi x, is Bayes-Nash incentive compatible BNIC, given limited misreports C if the expectation of the difference between v of theta I, pi of theta I, theta minus I omega, minus pi of theta I, theta minus I omega, which is greater than equals to the expectation of v of theta I, pi of theta I to the head, theta minus I omega, minus pi of theta I to the head, theta minus I and omega, for all theta I to the head, which is in C of theta, that the misreports of agent I, and for all theta I, where the expectation is taken with respect to the distribution on types theta minus I and stochastic events omega and any randomization within the policy. BNIC is a weaker solution concept than DSIC because it requires only that truth revelation is the best response when other agents are also truthful and in expectation given the distribution on agent types and on stochastic events in the environment. Remark the revelation principle. Commonly held intuition from offline MD suggests that focusing on the class of incentive-compatible direct revelation online mechanisms is without loss of generality. However, if agents are unable to send messages to a mechanism in period T which is not in the closed interval between AI and DI, then this is not true. Now let example 16.7 is the failures of a revelation principle. Consider the model with no early arrival misreports but allowed for late departure misreports. Consider two time periods, T, which is just among the simple set 1 and 2. A single unit of an indivisible item to allocate in either period 1 or 2 and an environment with a single agent. Denote the type of the agent, the tuple AI Wi with a Wi greater than 0 to denote its value for the item if allocated in period T, which is in chosen among the closed interval between AI and DI. Suppose that the possible types are 1, 1, 1 or 1, 2, 1. Consider an indirect mechanism that allows an agent to send one of messages, 1 or 2 in period 1 and the singular 1 in period 2. That singular 1 is with braces in period 2. Let phi denote a null message. Now consider the decision policy. Pi to the 1 of 1 is equals to 0. Pi to the 1 of 2 is equals to 1. Pi to the 2 of 1z is equals to pi to the 2 of 2z, which is equals to 0. For z is chosen among the set either 1 or phi, that is empty set. Now writing the state as the sequence of messages received in the decision k to the t, which is in the set either 0 or 1, to indicate whether or not the agent is allocated in a period t, which is in the set among 1 and 2. Consider the payment policy. X to the 1 of 1 is equals to x to the 2 of 1 phi, which is equals to x to the 2 of 1 1, which is equals to 0, and x to the 1 of 2 is equals to 3, x to the 2 of 2 1 is equals to minus 2.01. Note, this is very special value. And x to the 2 of 2 phi is equals to 0. Now type 111 will report message 1 in period 1 because reporting message 2 is not useful, and it cannot report messages to 1. Type 121 will report message 2 1 and has no useful deviation. This policy cannot be implemented as a DSIC, direct revelation mechanism, because type 121 is allocated in period 1 for payment 0.99, and so type 111, which is unallocated, if truthful, will want to report type 121. The revelation principle fails in this example because the indirect mechanism prevents the agent from claiming a later departure than its true departure. In fact, the revelation principle continues to hold when misreports are limited to no late departures in addition to no early arrivals. A form of the revelation principle can also be recovered by introducing simple heartbeat messages into a direct revelation mechanism, whereby an agent still makes a single report about its type, but must also send a non-informative heartbeat message in every period t, which is chosen among the closed interval of AI to the head and DI to the head. We leave the derivation of this revelation principle plus heartbeat results as an exercise. With this in hand, And in keeping with the current literature on online mechanisms, we will focus on incentive-compatible direct revelation online mechanisms in this chapter.